Okay, picture this. You take a piece of metal, completely bend it out of shape, crumple it into a ball, and then you just heat it up and it springs perfectly back to its original form. I mean, it literally looks like magic, right? These are called shape memory alloys, or SMAs. They're the driving force behind all sorts of tech, from those self-expanding medical stents they use in arteries to aerospace wings that actually morph mid-flight. But here's the multi-million-dollar engineering secret. While it looks like magic to you and me, for the engineers trying to build safe, reliable devices with it, it can be a highly unpredictable nightmare. Predicting this shape-shifting behavior mathematically is incredibly difficult. So welcome to this explainer. Today, we're going to unpack exactly how structural engineers and computational scientists teamed up to figure out the physical limits of these magical materials, and in the process completely flipped a century of traditional metallurgy right on its head.
Okay, let's dive into this. Here is our roadmap for today. 1. The shape memory problem. 2. Failing traditional models. 3. Enter the strain space. 4. Mapping the yield surface. And 5. Computing the future. Section 1. The shape memory problem. Or, as I like to call it, what happens when metals decide to completely misbehave?
So traditional metals, think standard steel or aluminum, they're pretty reliable. If you bend them past a certain point, they undergo permanent plastic deformation. They yield in a way that's predictable and uniform. But shape memory alloys, they undergo a literal phase transformation right at the atomic level. And a super cool trait comes with a massive headache for engineers, which is severe tension compression asymmetry. Basically, an SMA behaves completely differently when you pull it in tension than it does when you compress it. And for traditional engineering, that asymmetry is a total nightmare.
Let's put this into perspective to see the real-world danger here. Consider these two numbers, 0.30 millimeters versus 0.16 millimeters. Researchers ran a simulation on a long nickel-titanium shape memory tube, subjecting it to really intense inner pressure. First, they used the traditional math models, the ones that assume metals behave symmetrically. Those classic models predicted the radial displacement, how much the tube would bulge outward, would be 0.30 millimeters. But when they swap to models that reflect the real, asymmetric SMA behavior, the tube only displays 0.16 millimeters. Guys, that is almost half. If you're designing a life-saving medical implant or some high-pressure actuator, a 50% margin of error isn't just a tiny miscalculation. It's literally a catastrophic failure waiting to happen.
Which brings us to Section 2, Failing Traditional Models and the Limits of Mises.
For decades now, structural engineers have sworn by two gold standard mathematical criteria, the Truska and von Mises yield criteria. These models operate in what's called stress space. They're macroscopic. They look at the overall force applied to an object on the outside, and, crucially, they assume isotropic, symmetric material behavior. In plain English, they assume the metal yields symmetrically, whether you pull it, twist it, or squish it. But, as we just learned, shape memory alloys absolutely do not care about symmetry. Because von Mises and Truska totally ignore the microscopic phase transformations of smart materials, their predictions just completely fall apart.
So that leaves the engineering world with a massive, massive question. How do we model the unpredictable? If our best macro-level stress equations are spitting out dangerous results, where exactly do we look for the answer? Section 3. Enter the strain space. A total shift in perspective. The crucial point here is that if looking at the macroscopic stress on the outside of the metal isn't cutting it, we have to zoom all the way in, down to the atomic level. We have to look at the phase transformation. This is the structural shift of a crystal lattice from a phase we call austenite to a phase called martensite. And because this shift is an actual physical geometric change in the crystal structure itself, we don't have to guess how it behaves. The exact plastic strain can be calculated directly from those changes in the lattice structure. We're essentially moving away from that old stress space and stepping into strain space.
And as you can see here, this is what that shift actually looks like. We're looking at a nickel-titanium lattice starting out in this neat, body-centered cubic structure. That's the austenite phase. But when stress is applied, it shifts into a complex monoclinic structure, the martensite phase. Now here is where it gets absolutely wild. Because of the specific angles of the structure, the crystal can fold and transform into up to 12 different correspondence variants, basically 12 different ways it can microscopically yield. But researchers found a golden rule hiding in all this complexity. No matter which of those 12 variants the crystal shifts into, the driving energy required for that specific phase transformation is a constant. And that constant driving energy, that is the exact anchor we need to finally predict the unpredictable.
Section 4. Mapping the yield surface.
It's time to visualize the math. And this brilliantly illustrates the whole paradigm shift. You're looking at the 3D yield surface of nickel titanium, based on true lattice strain behavior, not those old stress models. Now, in traditional von Mises math, a yield surface usually looks like a perfect, smooth, symmetrical cylinder. Boring, right? But look at this. It's asymmetric, it's super irregular, it's got these sharp, jagged edges sticking out. This 3D map proves visually that shape memory alloys have vastly different limits depending on the exact combination of directional forces acting on them. It's just a beautifully complex terrain of material failure. But when we take a 2D slice of that 3D object, the failure of the old models becomes just glaringly obvious. Focus on this cross-section. Do you see that smooth, dashed circle right in the middle? That's the von Mises prediction. That is what traditional engineering assumes the boundary is. Now look at the solid line wrapping around it. That's the actual calculated strain space yield boundary for our SMA. It's a triangle. No way is that a perfect circle. In some directions, the SMA can handle way more force than traditional models predict, and in other directions, it handles way less. This single visual completely explains why that pressurized tube drum earlier only bulged 0.16 millimeters instead of 0.30. The old models assumed a circle, but reality? Reality is a triangle.
Section 5. Computing the future. We're talking GPUs and smart devices.
Now, knowing the yield boundary is a triangle is great in theory, but how do we actually apply this in real-world design? Well, to map out these triangular boundaries for thousands of individual microscopic grains inside a piece of metal, we need some serious computational horsepower. The math is just way too complex for traditional sequential processing, so researchers use CUDA GPU algorithms to do the heavy lifting. And this computation happens in 3 distinct steps. Step 1 is data prep. The system stores the exact crystal orientations of thousands of individual grains in the metal. Step 2 is parallel compute. The GPU unleashes thousands of threads at the exact same time to calculate the stress-induced work for all possible martensite variants in every single grain, hunting for the maximum work value. And step 3 is aggregate. The system sums up these maximum values and averages them across the entire crystalline structure.
Finally, the GPU translates all those raw calculations into actionable engineering maps. By computing the average work for a specific stress state and then comparing it against a simple baseline, like uniaxial tension, the computer generates a normalized ratio. When you plot those ratios across all dimensions of stress, you get exactly those triangular, asymmetric yield surfaces we were just looking at. Boom! We now have a precise computational recipe to simulate the exact physical boundaries of shape memory alloys under pretty much any condition. To wrap up our journey from macroscopic stress to microscopic strain, I want to share a quote directly from the source material. It says, "Instead of based on stress, it is the yield mechanism and the associated yield strain that determine the yield criterion of a material." This is absolutely the core takeaway of this explainer. To truly understand and use smart materials, we have to stop just looking at what we're doing to the outside of the material and start looking at how the crystal lattice on the inside is mechanically shifting to deal with it. By combining advanced metallurgical theory with the parallel processing power of modern GPUs, we've basically cracked the code of shape memory alloys. We don't have to guess anymore. We don't have to rely on century-old models that get things dangerously wrong. Which leaves us with one really exciting question. What incredible, shape-shifting, smart devices will we build now that we can accurately predict their physical limits? The possibilities, whether it's robotics or cutting-edge biomedicine, are absolutely endless. Thanks so much for joining me on this explainer, and I will catch you in the next one.